a teaching assistant at the Textile Engineering Department and Faculty of Engineering at Alexandria University, also here in Egypt.
Application of artificial neural networks in fabric design and identification. This paper is prepared by myself, Engineer Khamy, a teaching assistant in the Faculty of Engineering at Alexandria University, and Professor Dr. Messiry, the head of the Textile Engineering Department. A quick history on the woven fabric design. As for the traditional methods, the designer's capability was always dependent on the production of fabric plus samples in order to illustrate his own designs. As for the present decade, the introduction of CAD systems has permitted the simulation of fabric and textural appearance and presentation of special effects such as drape on the computer directly, and it has also permitted the creation of libraries for most of the standard weave designs common to be used in our industry. But the main demand of a successful CAD system was the presence, number one, of a weave analysis system. What we mean by a weave analysis system is that each fabric design is analyzed into a matrix, a two-dimensional matrix, where the coefficients of this matrix is binary values 0 or 1, 0 representing the intersection of the weft yarns over the warp yarns, and a value of 1 representing the intersection of the warp yarns over the weft yarns. A main necessity for a successful CAD system was the presence of a weave coding system. Why a weave coding system? Because if we just input every value of the individual cell of our design by a 0 or 1 value, first it is so time consuming, and second, the user may get complicated during the input of these values. So we had to have another way of inputting the values by using the weave coding system, and Messiry had developed a weave designing coding system where he analyzed the weave designing into a successive operations, and he gave each designing operation a certain code, and then the design is revealed through a finite succession of codes. But according to using a weave coding system, not any user could use a weave coding system, and he had to be a human expertise. So the goal of our work was an attempt to replace the weave coding system by another simple technique, not requiring a human expertise, number one, and at the same way, it is simple and capable of introducing and identifying the different fabric designs to our CAD system for fabric simulation, or directly to a dobby, electronic dobby for weaving. Our attempt was approached by using image analysis and artificial intelligence techniques based on neural networks. Image analysis, interest in image analysis was always focused on procedures for extracting information from images suitable to be processed on computer. For example, if somebody sees any image and what is the information that he extracts from this image, and what is the most important information that he wants. Digital image presentation. The term image usually refers to a two-dimensional light intensity function, f of x and y, where the value of f of x and y at any point is proportional to the gray level of the image at that point. We mean by the gray level value that difference in every shade or color is given a gray level value, and the image would be translated in the form of a matrix of values of each shade at any point in this image. We usually divide the image into a number of elements. These elements are called pixels. Talking in brief on artificial neural networks tend to simulate the functioning of the human brain, but approximately in a mathematical information. This is a quick correspondence between how the human brain works and how a neural network works. We could see that they are very close in their functioning together. Application of neural networks have been applied in many fields of textile, and they have proved themselves to be successful in many of the textile fields. We could just mention a few of these applications. For example, there was a worsted fabric system used for prediction of fabric properties. And neural fuzzy modeling was also very successful in prediction of fabric handle values, and many others have been working in the very fabric handle values to be predicted by neural networks. Also, a neural network model was used to predict the properties of knitted fabric from knitting machine parameters. This was actually my BSc project done by me under the supervision of Dr. Adil. Artificial neural networks is actually a set of networks consisting of a massive number of processing elements. These processing elements are usually known as neural nodes, where the neural network consists of a set of layers. Each layer consists of a number of neural nodes. As for the input layer of my network, the neural nodes will be equal to the number of inputs I input to my neural network. As for the number of neural nodes in the output layer of the neural network, the neural nodes will be equal to the number of the outputs I require from the neural network. And as for the number of neural nodes in the hidden layers, these are usually determined by trial and error till we reach an optimum performance of the neural network. These neural nodes, each one of them receives an input from XO to Xn. These inputs are further multiplied by something we call weights. These weights are usually randomly selected values ranging from 0 to 1. Then this weighted output is further processed by a function we call an activation or a transfer function to produce the output of each neural processing node. It is the activation function or the transfer function which determines the form of our output of the neural network. For example, if we use a linear transfer function or activation function, our output of the neural network would be derived from negative infinity to positive infinity. If we use a hard limiting activation function, such as the one restricted, our output of the neural network is either 0 or 1. If we use a sigmoidal activation function like this one, then our output is ranging from 0 to 1. Not like this. This is either 0 or 1. This is ranging from 0 to 1. This is a log sigmoidal transfer function. We could also use a tan sigmoidal subprint function where the output would range from negative 1 to 1. In our work, we use the learning algorithm, a backpropagation learning algorithm. The main feature of this learning algorithm is that the actual output in each training trial of the neural network is compared with the target output of our neural network, and the error is calculated. We calculate something called the mean square error. This mean square error is backpropagated through the neural network and is used to adapt the weights once more in order these weights which were initially selected randomly, and then these adapted weights are used in the following trial, and this goes on through all the trials till we reach the minimum error required. Our proposed system is that we use hand drafts of different fabric design, and these hand drafts are introduced to a scanner, and then we go on our processing through a PC, and then the output of the PC is presented to the electronic dobby. Building the system. Step number 1 in building the system is that first we introduce the hand drafts, our hand drafts. We used 18 different hand drafts of fabric designs, those most commonly used. These hand drafts were introduced to a flat bed scanner, and the images were acquired using a resolution of 200 dpi, and we saved them by bitmap images. These are the different hand drafts. We can see that they are hand drafts, so they are not perfectly, the straight lines are not so perfect, and there are certain noises in each of the images. We can also recognize that because we are using different designs, the size of repeat of each design is different than the other, so accordingly the size of the images acquired will be different. Most of our images acquired, the size of these images were ranging from 230 to 230 pixel image. So a 230 pixel image will accordingly, if each pixel is given a gray value, the resulting matrix will be a 230 to 230 dimensional matrix. If this matrix is directly introduced to our neural network, then we would require 230 to 230 neurons in the input layer of our neural network. This would require a very complex neural network and would take a very long time in training. So in order to simplify our neural network, all the images acquired were reduced to a 32 to 32 pixel image. We found that it was a convenient size, and it at the same time maintained the main feature of each image, so that the neural network could easily recognize the images. Taking a diamond tool as an example, it was a 293 to 293 pixel image when it was first acquired, and we had reduced it to a 32 to 32 pixel image. Second, we can also not take this matrix, the resulting matrix can also not be introduced directly to the neural network, because as we will take the diamond tool still as an example, this is the resulting matrix, the 32 to 32 pixel matrix. We can see here that it should be a binary value image, where the black pixels give us a gray value of 0, and the white pixels give us a gray value of 255. But we see here, since we are dealing with hand drafts and different shades during quick hand drafts, we see here that we have different values of 1 and 2 and 87. So this image has to be transformed to a perfect binary matrix first, to a 0 and 155 binary valued matrix, and then a second thing, also this binary valued matrix of 0 and 155 cannot also be introduced directly to the neural network, because if we have very big differences in the values of the variables input to the neural network, for example, we had values 0 and 255 like in our case, the error due to each input value will not be, the effect of each error will not be the same, because in each training trial we said that the backpropagation neural network calculates the error of each input and compares it to the target output and calculates the error. So we can reduce that the error due to the large valued variable, which is 255, will be, its effect will be greater than that due to the low valued variable, which is 0. So we transformed all the gray value of 255 to a 0-1 matrix, a binary 0-1 matrix, which should be the ideal gray level matrix representing this image. Step number 5, we had to set the output of a neural network, what would be the shape of our output. So we decided to give every fabric design a special code. A special code, this code could be any number, which could representing the output of a neural network, but we tried to give it a binary code, a 0-1 code, in order to simplify the output of our neural network. Construction of our neural network, the best results were given when we used one hidden layer with 20 neurons. As we said, the number of neurons of the hidden layer are known by trial and error. As we mentioned before, we use the backpropagation learning rule, and we use the log sigmoidal function because our outputs are 0 or 1, so we don't need a linear or a pan-sigmoidal activation function. And the training parameters, we set the learning rate at 0.75, and we set it adaptable with an incremental and decremental rate so that it is sensitive to the error produced. And we set the error goal to 10 to the power -3, which we found that it was very convenient to us. And the training was up to 1000 depage, and the momentum constant we set at 0.75. The advantage of setting the momentum constant is that it prevents our neural network from being trapped in a local minimum and keeps on searching along the error surface till it reaches a global minimum of the error. The output of our neural network is the coded matrix we had decided before. And the training results of our neural network were that our error goal was reached, and in a relatively very short training time, in only 194 epochs. After training our neural network, we had to simulate it. Simulation was done by first passing all the training sets once again through the neural network. And the target data was plotted against the model prediction, and here we can see that this is the target data and this is the model prediction. We can see that all the lines lie about 45 degrees, which means that the target output is nearly equal to the model prediction. We now tested our neural network by introducing hand graphs with different noise levels. For example, if a user just quickly wants to scratch any hand graph and introduce it to the neural network so that the dobby could quickly perform this weave. And our neural network successfully recognized all these weaves, and there was no error produced. Now the output of the system is that we take the coded image that we had previously mentioned, and then this coded image, this coded matrix is transformed to the ideal gray level matrix, which we had produced before, and this is the output of the system, which is then presented to the electronic dobby for weaving, or it could be presented to a CAD system for fabric simulation. Another use of this identified weave design is that it can be used together with the hand draft of a drawing in draft, which is also in a very similar way identified by our neural network, and it could be used to obtain a new design as required by the dobby, and it could be used to produce very large repeats of design as required by us. Conclusions: the system proves to be capable of identifying various fabric designs successfully, and we have made use of the learning capacity and the fault-tolerant nature of the neural network by using backpropagation. And the neural network, together with image analysis techniques, can be used as a very good online classifier for fabric design. Suggestions for future work: we could enlarge our system identification and produce a data bank for all the possibly required fabric designs. And our future work of my interest is to identify fabric designs directly from fabric samples instead of using hand drafts. Thank you for listening.
We may have time for one quick question. Maybe you have a question for the speaker? I think we're changing over the computer. I'm going to go ahead and introduce the next speaker while we're getting ready here. Our next speaker is Chaplin, who's an instructor at North Carolina State University, Department of Textile and Apparel Technology and Management. Her research interests include digital design and digital printing. Ms. Chapman also manages our state-of-the-art digital design center in the Textile and Apparel Technology and Management Department at the College of Textiles, North Carolina State University. Hello.
Good to hear me. Hello. I'm so happy to be here today. Happy because I can show you the work that we're doing at North Carolina State University, and also hopefully exchange some ideas and learn what you're doing in this area as well. I've been working in the area of digital printing for about 5 years now, And what I'm going to show you today is a model that we developed at North Carolina State that we think really capitalizes on some of the abilities of digital printing. The reason that we're exploring this model, we're exploring digital printing, is there's a demand for it. Some of these demands are, we have a society now where most of our consumers are very immersed and very knowledgeable about technology. They're very ready to be part of the design process and ready to be immersed in some of this computer-aided design. And also the fashion cycle has really speeded up. It's become much more individualistic. People are very knowledgeable about what they want from clothing, and they're very demanding about that they get what they want. Another advantage of this model that I'm going to show you is that we're able to have a more centralized product development process and manufacturing. And the last one that I'm very interested in is that when we are working with this digital printing model, we're really able to better marry the apparel and textile design. The first model that I'm going to show you is one by Messiry. Messiry is a Japanese company, and they're working in whole garment knitting. So it's a little bit different than what we're doing, but their model is very applicable to what we're doing. The first part of their personal order system is a sample book. A customer could go into the store, look at the samples, pick out knitted design, color selections, then look at the design library, look at the shape of the garment, pick out a certain shape of the garment, and then have that garment fitted to them. They're then taking a photograph and virtually modeling or simulating what that garment would look like. And this is all before the garment is created. Once the customer approves the design, approves the simulation process on the modeled garment, then production happens. And that's a very rapid process within a matter of hours. And of course, the final end product is the finished garment. Some of the benefits of this model are rapid customization, the 3D visualization, again, where the customer is actually able to see the garment modeled on them before they purchase it, and then the integrated design process where the shape of the garment is really integrated very well with the garment design as well. This is the model that we're working on at North Carolina State. It's very similar to their model, but we're using digital printing, obviously, rather than knitted design. And what we're working on is building an archive, a digital library of some of these printed designs and apparel designs. And instead of the photograph, we're using 3D body scanning. For 3D body scanning, we're able to model the garment, and we'll be able to better fit the garment. And I'll go through step by step of this process also. And some of the key differences, again, we're using the digital library rather than the sample book, and again, we're using the 3D body scanning for the photograph. This is the first step in the design process where we're building the design libraries. This is actually a photograph of Khany's garment, and you can see that was digitally taken, and then we're extracting some of those images from that and building this into our design library. The iris, the sky motif, and the dragonfly. These images that we then collected in this archive, this image archive, then become flexible design units of transparent layers that we can layer onto each other to use for further design. And this next clip is just going to, a little bit difficult to see, but this next clip is going to show you how these transparent layers are merged to form these textile designs. You see we have stripe pattern and then the texture and the motifs. They're layered on top of each other and merged together to form more complex designs. The flower in the bottom left-hand corner was actually a flower from my garden that I scanned into as part of the library. And then once we've created these designs, of course, in CAD we can very quickly change the colors, change the structure of the textile design. But after the consumer has gone in and picked out the textile design from the image library, they're then able to go into the apparel design library and pick out the garment shape. And you can see very quickly they can pick take a base pattern and change things such as hemline, change the shape of the neckline. And then the next step would be the three-dimensional body scanning. This is a 5-step process. The whole process takes about 53 seconds. The first step is where the body is positioned for scanning. We normally have them change to exercise type apparel. White light is reflected off the body. And then a 3D point cloud is generated. From this 3D point cloud, landmark points are determined, and then we're able to extract the measurements. We typically extract a possible 141 different measurements. We may need 40 measurements for a typical garment construction. These body scan measurements of the consumer are then entered into the apparel design program where the pattern, the marker pattern is created. And this is where we then take this pattern that's created, the marker layout, and then start taking those images that we've chosen from the digital library and filling them in. The first step would be to fill in that background layer directly into the pattern. And then we start adding the images. This is the typical image that would be chosen from that library that's added to this garment. And we can also layer different patterns on top of that as well. This is the detail of one of the garments that's produced this way. It's difficult to see here, but all of these patterns will flow seamlessly across dark seams and closures. And you'll note that very different than screen printing, we really have the capability of getting fine line details, radiance, and an almost photographic type quality of the fabric. This is a simulation of the garment, and this is the actual garment created. You can see what we get is an actually panoramic print around the whole garment shape that goes around the three-dimensional body. This is another garment that we produced. This is the marker that was created, the textile design is created inside of that. And if you notice on the far right that the detail of the dress, this was done for a visiting student that was leaving, going back, and her friends signed pieces of paper. We scanned them into the computer and actually incorporated those handwritten designs into the garment. And we're also working not just on apparel, but this could be applicable for home furnishings. This was actually an interior window treatment, a canvas awning treatment that we did for an area restaurant. And some of the images that we pulled from the library were a pattern, a type of column, and then the restaurant themselves provided us with a logo that we then put into that design, and we're able to integrate that into the finished product. Are there any questions for the speaker?
Please, what do you make by scanning for the measurement for your system?
Pardon me? Oh, we're using,
Scanning measurement for this.
right, the scanner that we're using is TC squares. Sometimes you hear it as an image twin scanner. It's a white light technology. Yes.
Hello, yeah. First of all, I would like to thank you for such a nice presentation for us. Anyways, well, you were discussing about that pattern making. You just get the pattern out, patterns out on scanning. Is it possible that can we combine it with the computer and then we can use the same pattern for automatic cutting of apparel as well?
Yeah,
Is it essential for your project?
we're using an electric system to create our patterns, our markers for this, and we can send those to an automatic cutter if we want to. We have a lot of skewing and distortion of the fabric. So
Yeah, that's what I want to know, because that's what I want to know about the error percentage. Is there any error percentage discussed? I mean, have you been researching about that?
We've been trying to collect data on different fabrics that we're using. We mainly use cellulosic fabrics, silks, and cottons, and some linens. And because a lot of them are paperback or skewed during the pre-treatment process, there is a lot of skewing. We normally have more skewing in the length than we do in the width. It's usually about, on average, about 10% and 3% in the width.
Yeah, you're right, but I believe that you should incorporate, the software has to incorporate the actual screen data and actual fall data from the fabric you're getting from, the gray fabric. And in this way you will be able to just, you will be able to imply the design in a more realistic way. Like the simulation, the real thing, it will be more similar. So I think that should be worked on.
Yeah, one of the other things that we're looking into also is preventing some of the skewing or shrinking as well. We have some chemists at North Carolina State that may be able to help us with that as well.
Okay, thank you.
Thank you very much.